All right, so my name's Samakana, and I'm going to talk about using embedded Python for sensor networks. So this project started, I used to be at the University of Cincinnati, or it was before that. So I was between jobs, and I met some people at a party, and one of them was a PhD student in geography, and he was working on sensor research. He had done a lot of stuff in the Arctic with his former professor, and currently they're trying to make low-cost sensor relays. So normally a lot of environmental sensors are pretty expensive. They cost a couple $1,000s. A lot of them are set up to be able to withstand attacks from bears. I mean, they have to survive out in nature. But the sensors themselves were fairly cheap, and we're trying to use just embedded systems running OpenWRT to power these sensor networks. And so the city of Cincinnati, where I lived at the time, they have what's called a combined sewer system. So there's sewage from households and rainwater, stormwater runoff both go into the same grates. Ooh. And it's actually pretty common. About 700 cities in the U.S. have combined systems. Thousands of cities around the world do. There's an advantage to them because since you have all your stormwater runoff going into the sewage system, you can treat all your stormwater runoff. And rainwater has tons of sediment in it. It has silt. It has pollution. It has all kinds of bad stuff. The bad part is once you get so much rain, it backs up and you have to have an overflow, so it gets dumped straight into the river. It's diluted by a lot of the rainwater, but you are still getting raw sewage dumped into rivers. Cincinnati was bad enough, their piping was bad enough that it started backing up into people's homes. The city of Cincinnati got sued, and they lost their lawsuit, so now they have to clean up any spillage that happens in people's basements. They actually had to send us all refrigerator magnets to remind us that they're responsible for it. And so they needed to stop the amount of water going into the sewage grates, and they wanted to test permeable pavers that would allow a lot of its water to go into the groundwater supply instead of going directly into the river. So this is an example of a combined sewer overflow. Let me play this video. So you're talking about megaliters of water. This is actually probably about 2 days of rain, not a horrible rain, so quite a bit. And so these grates open up once the water gets past certain point. A lot of these grates have been ripped off just over time. And that combines stormwater and raw sewage. I wasn't out here for this. Some school of others out here. So it's mostly around. Right? And so there's where you see a lot of the actual sewage. So, sorry, what's the question?
I missed the part where you were saying where this was.
Oh yeah, so this is one of the overflow grates that goes into one of the levees. So that's combined sewage and rainwater. So the Civic Garden Center was a nonprofit organization in Cincinnati, and they had this area that used to be a petrol station, changed into a car park, and they were going to use this as an experiment center. So we were going to have 6 different segments with different permeable pavers set up, and each segment had lining on the sides, they had lining on the bottom, and they had a sewer grate at the bottom. And so the sewer grate would fill up with water, we'd have a pump that would trigger, and then we'd flush all the water through and calculate how much water actually went into the sewer grate versus how much went into the permeable paver surface. We used OpenWRT, an embedded Linux operating system, and one-wire sensors. One-wire sensors, they're really neat. They only have 2 wires going to them, the power wires, and they transmit power and data over the same line. So that's why they're called one wire. You can chain them together and have several sensors on the same wire. They're a little bit slower than other sensors. They take 2 or 3 seconds to respond. Longer if you have more sensors on the wire, but they are low cost and low power.
Sorry, before you go on.
Yep.
Can I just get one thing clear? So what the aim is to stop the water going into the drain, but instead allow it to get into the ground.
Yes, and that's so that.
And normal pavers would just go over the top of, so it'll end up going in the grate and into the river and stuff.
Yep. So on this pavement surface, this center one right here, this is actually concrete. So that's our control. That's what normal concrete does. It's non-permeable. All the water that falls onto concrete should go directly into the sewer grate, so it should have the highest amount of water in it. All these others, there are 2 types of permeable cobblestone. There's a third one up here, but it's at the wrong angle, so we didn't count it in the study. 2 types of permeable cobblestone, permeable asphalt, and then permeable concrete next to it. And that's the one we couldn't use. And so all of our sensor relays were actually back in the station. This is also, it was a nonprofit organization, so they did a lot of stuff with the community and taught lessons and had a lot of green stuff, such as green roof, this rain storage tank. Here's a top view of the car park as well. So each of these zones was about 8 by 14 meters, and each one had beneath the surface they had 3 layers. All of them were about 3.3 meters tall, or 1 foot tall. One was of cobblestized rock, and then of pea gravel, and then of cobble gravel. So all 3 of these zones were set up the exact same way. And here's an overview of where all of our sensors were laid out. This is from ArcGIS, and we used the GPS, Tremble GPS, to get exact locations on each one of the sensor types. So there you can see all the pavements and the overhead map. This is just a regular old Linksys router, and so we reflashed these to run OpenWRT. So you can see the one-wire dongle on the end. The temperature sensor is up here at the top. That's the temperature sensor. And so this is just a regular home router that you'd use that we'd reflash to run embedded Linux and run a Python interpreter on top of it. This is the idea of how the pavement was supposed to be laid out. This is an old diagram. This is nothing what it actually looks like today. But the idea was that you had the sewer grate, we'd have our sensors in it, and then we had this pipe that went all the way back to that main research center where we pull in all the sensor data. These are the actual routers. These have all been reflashed with OpenWRT. We got some routers that were pretty nice. They had 16 megs of flash on them. Most of your home routers only have about 4 megs, so you can't really flash new Linux onto them. They're pretty tightly packed. The good ones you can find have 8 megs, and it was really hard to find ones that had 16 megs. 16 megs is really good because the Python interpreter is, I think, 5 or 6 megs by itself. And here you see the one-wire dongles on each one of these routers on this USB hub, and also a USB flash drive, which we stored a lot of data on. So this is the data flow. We have our one-wire sensors. It goes to these one-wire dongles. Then we have a Python application that encodes data in XML, possibly stores it in a buffer before it goes out to the web service, and then from the web service to web applications. For this presentation, we're only going to be talking about the stuff on the left, everything in red and orange, which is the Python piece. So the framework that I designed is called LtSense. And so this framework had controllers, it had data handlers to handle the one-wire protocol, had identifiers so that we could uniquely identify our routers, transport handlers, sensors, queues, and security. I'm going to go through all of the components and then show how they're kind of glued together. So the controller is really basic. So most sensor networks work on a sample rate. You give it a sample rate and they take so many samples per day or so many samples per hour. A lot of the sensors that we looked at and we found in papers had really low sample rates, usually like 4 or 5 samples per day. Since we had direct power and we had direct Ethernet, we didn't have to worry about batteries. A lot of them were low just because they had to power on, do their sample, and then power back off, so survive the whole day. For this particular program, we set a sample rate of just 1 per minute. And so our basic controller, so notice a lot of these are, so we have this abstract controller, and there's really only one implementation, the default controller, which starts the base thread. The abstract controller takes in all of our components, such as data handlers, sensor handlers, transports. These are all added to it using dependency injection, which we'll show later. And then it just runs and goes through all the sensor handlers and grabs all the sensor data and sends it into the transports. There's also a respawning controller that if it finds a problem in production, it will try to respawn it in case there's an exception. Then it has a limit, a respawn time limit, so that it will only respawn so many times before giving up. So we also need an identifier. We need to be able to identify these relays that are sending our sensor information. So there are 3 types of identifiers we implemented. One was just using the MAC address, and that one's shown below. By default, grabs ETH0, and this is how you grab the MAC address in Python using just pure Python code. We also had a UUID identifier, which uses the UUID class in Python to create a GUID or UUID. And that way, if we had a lot of routers, we could use this, and we just auto-generate these UUIDs. Which, if you've seen them before, they just look like long random unique strings. And then we also have the named identifier, where we just give it a set name. For the project we're on, we just gave them all names because we only had 8 of them, so we could just name them of what they were, 1- permeable concrete and so forth. So the abstract data handler is we want to make this, we were debating between having the routers actually encode the data in various formats or doing it on the web service end. We eventually did it in the web service. But the idea is that you could take this abstract data handler and just implement different types of data encoding mechanisms. So we created our own XML structure for it, but you could also extend this and use it for JSON or encode WaterML, which is a common standard markup for sensor data. So this was just using our standard proprietary XML format. We're just using mini-DOM to create our XML object. And this is what our XML actually looks at. We have an aggregator, we have a package, and the package contains a Unix timestamp, the identifier that we specified using the identifier class, and then all of our sensor data. So we have volume, flow rate, and temperature listed here. We also have this signature at the bottom, which I'll get into. So in our case, we signed all of our XML. We didn't send it over SSL, we just sent it plain text, but we signed everything using an RSA key so that we could ensure that the data we were getting was actually from our particular relay. So there's this abstract transport class. So the idea is we wanted to be able to transmit this in a lot of different ways. We're using HTTP because it was going to a web service. But you could basically take this abstract transport class and implement FTP. You could implement Dropbox. We had a Dropbox implementation, so we could actually send the XML or whatever we want to encode the data into directly into a Dropbox folder. So we had this base queued transport. So the queued transport had pause rate and a timeout. And so basically everything would extend that queued transport. So the queue would have one of the queues put into it, and it would store data, and then the transport will pull the data out of the queue and send it this way. So this is the basic HTTP transport, which implements pulling data out of the queue and sending it over HTTP. Pretty straightforward. And here's, so anything can implement that queue transport, and we just have to implement the run transport function. And here's the run transport implemented using the URL lib. So we also have this queue. So the idea is that if we lost power to or if the server went down, so if we had no place to send the data, the router should be able to queue up all of this data and then send it all later. So we added a queuing mechanism, so the queue gets injected into the transport layer. And so the most basic queue is a memory queue, which just uses the basic queue class in Python and holds everything in memory. And then we also had an SQLite queue. So with SQLite, we just put it onto the flash drive, and that way it would also survive a power outage. So if the power went out and it came back up and it wasn't able to transmit all the data to the server, it would then flush out that queue and send all that data to the server. So here's a SQLite queue. It's pretty basic. It implements the same functions for enqueue and dayqueue. Overrides the size property and pulls it straight out of the SQL table. Notice that when we create this, we set at the top check same thread equals default. So by default, SQLite 3 checks whenever you use one of its functions to make sure that it's being called by the same thread ID that created it, because it's not thread safe. And because I was using two different threads in this case, one to queue up the data and one for the transport, we had to implement our own locking. So as you can see, around each one of these functions, there is a SQL lock acquire and a SQL lock release. So that's just a standard lock object. And so we turned off thread checking and then did our own locking here. So, yep.
Did you have SQLite doing transactions? Because I was thinking without them, the power off would be a little dodgy.
No, we weren't. So that would be kind of interesting. We didn't have any problems with this that I know of. Yeah, no, we didn't. So we're taking everything at a constant sample rate, so it's one sample per minute. So because of that, we're not actually having any two things write to the database at the same time. So it's really more of the reading and clearing it out. But yeah, there could have been problems, corruption there. We didn't. Not that I know of. I don't think we encountered anything. So security was pretty basic. We used RSA keys to sign everything. I looked at using M2 Crypto, PY Crypto, and the RSA library within PyPy. M2 Crypto and PY Crypto are both C Python modules, so we had to compile them for OpenWRT to use them. PY Crypto, we were able to get the compile, and it worked sort of. It signed everything. I could not get the web service in Java to verify any of the signatures. I couldn't get any other tools to actually verify the signatures. So for some reason, the version of PY Crypto we're using either didn't use the right padding, we're not really sure. But I gave up on that. M2 Crypto worked great, straight out of the box. I could verify all the signatures in Java. Fortunately, we couldn't get it to compile with the OpenWRT toolchain. And so finally we looked at the RSA library that's in PyPy. It's just called RSA. And it doesn't have any native code in it, so it has no C Python bindings. So that means it's slower than the other two libraries. But it worked fine. It worked in Python 2 and 3. And our tester that's written for the web service was written in Python 3. And because we only had a sample rate of 1 per minute, the speed wasn't really a problem. So we went ahead and used RSA. For Java and Scala, Java has built-in support for RSA. That would have been fine, except that Java doesn't have built-in support for PEM files. We would have had to use a key tool in order to convert the PEM files. So I use Legion of the Bouncy Castle in Java. On my blog, penguindreams.org, there's actually a tutorial on how to get this whole process to work, signing things in Python and verifying it in Java, and the other way around as well. It covers M2 crypto and Legion of the Bouncy Castle. Doesn't cover the PyPy RSA yet. Been meaning to add that. So the RSA security is pretty simple. If there's no key found by the directory you give it, it generates one, saves it. If it is, it pulls that key up, and then it just signs data as it comes in with the key and then sends it out. And so here we have our two implementations, M2 Crypto and PyPy. The one we're seeing is the PyPy RSA implementation. So all of this is for the sensors. So at first we use, OneWire, there is something called one-wire file system, OWFS. Are any of you guys familiar with LUFS, the Linux userland file system at all? Some of you? So the Linux userland file system, so before userland file systems, say that you wanted in Linux to be able to connect to FTP and treat it like a real drive, you'd have to use FTPFS, and that was built into the kernel. And if you wanted to access an SSH share, you'd have to use SSHFS, which was a kernel module. So anytime that you wanted to implement one of these file systems, you'd actually have to implement a kernel module or have it compiled directly into the kernel, which left a little bit of flexibility out of it. And so LUFS was a project, the Linux userland file system, that created a thin layer on the kernel, and they had a kernel module. And then any program running as root could connect to it and implement their own file system in user space. And so that allows you to create virtual file systems. You can write them in C, you can write them in Python, whatever you wanted to. So we used one-wire file system and mounted the one-wire files. So every sensor we plugged in showed up as a file. We could go to a directory, which was the sensor ID, and just read the temperature file, and we could get a temperature reading. The trouble with it was pretty slow. And one-wire sensors were already pretty slow, so I just chalked it up to it being due to one-wire. Some of the readings took 8 to 10 seconds. Then we had someone on our team implement everything in C, and it took about 2 seconds. So it was pretty significant. He wrote a small program in C that I just called by command line in Python to get sensor readings off of it. And eventually we just wrote a C Python wrapper. So everything was, or C Python module. So everything was actually done in Python. And it made native calls to the one-wire libraries to get data out of there. I also wrote a camera module for one of the proprietary cameras we had, which was another C Python module we had in the project. So here are the actual sensors. So we have a couple of virtual sensors. These are just for testing. So they create random data, and they're just used in a testing environment when we don't have real sensors. For the actual sensors, we have this abstract one-wire sensor. The temperature sensor is pretty straightforward. You just grab a temperature. We also had, so for our fluids, so the way that these sensors work is as water is getting pumped out of these pits, it goes through this tipping sensor. And so every time a specific volume, I think it was like 2-point-something liters, went through it, it would tip. And so that meant that that volume of water went through. Well, for rain gauges, most rain gauges work this way too. I think it was 1/100th of an inch. I'm not sure how much that was in milliliters. But every time it tipped over, we knew that that volume of water had flowed through. So these counting sensors were kind of interesting because they were kind of calibrated differently. They depended on the volume that was on the actual bucket that was connected to them. So we had this base counting sensor class. And so for fluid volume, it was pretty simple. You take the volume of the bucket, multiply it times the number of clicks that you have. That gets you a fluid volume reading. But for things like flow rate, you need the previous reading. Same thing with wind speed. So for wind speed and flow rate sensors, we had a history counting sensor that kept track of the last measure and took the differential of the two. So one count minus the other times the coefficient. So here's our basic abstract sensor. All of them had IDs, types, data, and units. And so all these had to be implemented going down the chain. There's our standard exception. And then the standard sensor handler would contain a list of these sensors. So here's the basic abstract one-wire sensor that would read data. Here I'm calling it external process. This was the first process that we talked about before we made a native interface. And just send it a command and then read the response. Temperature sensors were pretty simple. Temperature units were in Celsius. Our basic counting sensor. Here's our history counting sensor where the first time we stored a measure, that would actually get saved to a file so that we could always read that back up the next time it started off. And then we had our duration, the current, and we took the delta and returned the delta. flow rate sensors were an implement of the same thing. So here we have a read bucket data and return volume divided by the time interval. Wind speed sensors used a coefficient. This was really specific to the wind gauge we had. So it was the delta divided by the sample rate divided by 2 times this coefficient for miles per hour. And then here I convert that to kilometers per hour. So how is all this glued together? We have all these components. And so there's this idea called dependency injection that you usually see in other applications. I remember being on a Python chat room talking about dependency injection. I showed them my implementation. They're like, you're missing an abstract singleton proxy bean. Like, seriously, what's that even do? And if any of you have seen Java or Spring implementations, you'll see crazy stuff like this a lot. And it's like, what's this do? I wanted a really simple dependency injection framework. So I've created one that only used the configuration parser within Python. And so there's this thing called loader.py in the applications. This is both in LtSense and in the BigSense tester. And so all the classes are actually wired together from a configuration file. It uses the config parser as its dependency, and I later split this apart into something called Diject. And so Diject is now an independent project, and it works in both Python 2 and Python 3. So this is how the basic dependency injection looks. So here we see our controller at the top. So we have this attribute called class. Class is special. It actually defines the exact name of the class we're calling, in this case controller.default controller. So anything else is just an attribute. So it's set on that class as if it were a property. So it's just calling that instance dot whatever and then setting, in this case, the sample rate, it sets it to 60. If there's a class ref after this, the class ref means that it takes another class that's defined in this file. So if we look down at agredata, the identifier takes in a class ref named identifier. So then it goes to named identifier, constructs this object, and then sets it to on that property of that object, which is an agredata handler. If they're curly brackets, it uses this as a list. So for transports, it actually supports multiple transports, so it'll go through each one. So here I only have one transport, the queued HTTP transport, but you can also have lists of things here. I will send those on. And here we define some static values such as units. The bucket volume is what I talked about. So when you have a tipping bucket, it needs to be calibrated for whatever the volume of that. In this case, this one, it tips over at 0.28011 liters. So this was split apart into Diject, which I just released last week. So Diject is a little bit more sophisticated. In the previous example, all of these get set as strings, which is really bad because then I have to change them to whatever property they really should be. So for instance, that sample rate is coming in as a string, and then within the class I change it to an int. Diject is a little bit smarter. It actually, the right side of the expression, it sends into the Python interpreter and interprets it correctly as if it were a Python type. So here you can define ints, lists. The only things that are special are, of course, class ref and then class ref with a list. But all the strings in this case have to actually be coded as strings, and they're actually evaluated in Python. And Diject also has its own set of unit tests. So I've made sure this works against various versions of Python 2 and 3. So for the demo, so the original version of this used SQL Server for the service. I'm not going into the service, but there is another presentation on that if you're curious on it. The service was written in Java and Scala and runs on top of Tomcat. Let me go ahead and put this up. So I'm just resetting my database so that we only see the data that's going to be coming in. And delete the other login. All right, so there's this bootstrap file. This is the only file that has to be run, and then the web service updates all its own schema. So we'll go ahead and run that once. So I'm going to start up the service. And so it goes ahead and creates all of the schema, and then here's the actual LtSense Python application. So the web service is up. So if we go to this, so there's no current data in the web service at all since I reset the database. So we're going to run LtSense. So I don't have any actual sensors connected to my laptop, so I just have virtual sensors that create random data. And we're going to give it a configuration file called local config. We're going to put it in debugging mode with -d. We're going to tell it it's a PID file, which is used in int scripts so that we can kill it. Oh, and this is meant for Python 2, so there wasn't a Python 3 interpreter embedded one for OpenWRT when we were working on this, so this is set up in Python 2. And so here's a lot of debugging information of how the dependency injection is working, where it's actually putting in all of these classes into the given properties. And here's the actual data. So it's sending this virtual data, temperatures, volume, flow rate, and then the web service is picking up that data. And oops. So if we go to the web service, we see that listed here. There's also a BigSense tester. So this is the automated set of functional tests for BigSense. There are about 200 tests listed. Go ahead and run that again. And so that's all written in Python 3. It uses the same type of dependency injection framework that's used for LtSense. And so if we go back to our list, we can now see all the stuff that came from our functional tester as well. All right. So the web testing framework, I'll just go through that really quickly. It's written in Python 3. It uses test sets, which I created, and test sets can hold additional test sets. It has generators, success conditioners, couplers, and security. So the generators look just like the generators in LtSense. This one is generating the exact same type of XML, except it's putting in random data instead of data from sensors. There's several success conditions, such as the status code, number of columns, whether there's well-formed XML, searching for specific XML elements. Here's an example of number of XML elements where I do an XPath search. The bottom one checks for a specific text in the body. There's only one coupler, so whenever you post something to the web service, it gives you a location of where to get that data from. So this coupler basically takes one test that posts the data and takes that location and puts it in the request for the next test to retrieve the data. And it uses the same type of dependency injection. So we see the request type, the success conditions. Here you can see an actual list of success conditions within this list. Those are all classes that it checks through. This is for the aggregate stuff, so we see some more complicated tests, some that take ranges over periods of time. Okay, so there are a couple of limitations to the actual sensor network that we set up. So the experiment setup that we had set up itself. So I talked about these tipping sensors, and you notice that there were both volume and flow rate sensors. So it looks like two sensors, a volume and flow rate, but they came off the same sensor. So everything that was a counting sensor actually had two values, except for wind speed, of course. And the flow rate, which took the differential, and then the volume. So the volume by itself isn't really useful. It gives you the total amount of volume since you start the experiment. And all of the sensors in the actual sewage pits had watch batteries on them, so even during a power out, they'd keep their counts. And so the trouble is, you get the total number of volume since the experiment started. So since like March 13th, when we started the experiment, say in November, we see that so many 14,000 megaliters of water have passed through the sensor. That doesn't really mean a whole lot. So we actually had to take that and aggregate it. So within the web service, you can do aggregate calls and take the average, say get the total amount of water per day for a given time period, say for a month, and it'll actually break it down by day. But the other problem was that because it was a float-based sensor, so these pits would get a bunch of water in them. They'd fill up, they'd fill up, they'd fill up. They wouldn't actually get any flow going into them until the float tipped. And once the float tipped, it would pump all the water out. So we'd actually see several thousand liters of water at once, and then 0 from then on out. And so you'd see a whole bunch of water and then no water. Meanwhile, the rain sensors just give us a constant rainfall. So in order to get a good idea of matching up rain events between rain that came in through our rain gauges and going out through water, we'd actually have to look at things over the course of a week, sometimes further. So it was kind of a disconnect between how we're looking at the rainfall and how we're actually looking at water getting pumped out of these pits. We also had a lot of problems with interference. At first, we'd be like, how did 14 kiloliters of water get pumped out in a minute? That doesn't make any sense. But you'd be surprised. Next time it's raining, look at one of these grates, and you'll be surprised at just how much water goes into any one of these drainage grates. It's an immense amount of water. At first, we thought we were getting bad readings. We actually were getting pretty accurate readings. But then we did have some that were way off, like gigaliters of water, and we're like, that can't be right. And so there are a couple problems. We had interference. We found that some of these patterns repeated at a 60 hertz loop, and so we found that we were just getting interference on the actual electrical connection. It was the Green Learning Center. I think they had electric vehicle charging stations. They had wires routed for them, but they never actually, I think they ran out of money before they could buy the actual chargers. But they still had power going to them, so we were probably getting interference from that. We could have been getting interference from the hospital across the street, which was a cancer treatment hospital. So we ended up, they added a lot more shielding. We shortened their wires. There were a lot of other things that our site manager and our head engineer did, and we got rid of all the interference, but we got a lot of bad data with that. So we had to throw away a couple of months of that. We also had problems with backflow. Occasionally we'd see only a couple of milliliters of water coming back through. And it's like, this can't be right, because the pump should trigger and we should see all the water go through. And when we got these small readings, we figured that water was actually coming back out of the bioswales that we're pumping the water into, back into the pits, and causing the counter to flip the other way. We also had a problem with the stoppers. So within each of these pits, there are these huge stoppers that went out to the bioswale. So we pumped all the water out into the bioswale, but the engineers who made these made them like they would any standard car park. So it had a lot of the standard stuff that you see in car parks, and they had all these standard safety mechanisms to prevent overflow. And the trouble was that some of these stoppers, there would be so much water in this bioswale. The bioswale was only about as wide as this table. It wasn't nearly wide enough to be able to soak up all the water and let it evaporate. So a lot of it would pile up and actually pop these stoppers off and start flowing back into the pits. The center one was the worst because all of the water would come straight down to it. So on our control, we would see several gigaliters of water going even after rain had stopped. And the trouble is we had an infinite loop of water, like a literal infinite loop, constantly pumping out. So that was a huge problem that we had to work through. There are also all these interesting vestigial components, things that we needed to get rid of, such as the command line one-wire client. So after we implemented the native interface, all of my old classes were still used to just single lines coming back in from the command line. So even with the native interface, I just created a thin wrapper that took in those standard string commands and translated them to native functions. So that still needs to be rewritten. Also, the counting sensors, we had this idea of moving the whole calibration of the counting sensors into the web service. So instead of getting flow rates and volume straight off the sensors, we would actually configure that in the web service. And that way we just get a count. And that way we wouldn't have to worry about calibrating the routers. We could just toss routers out there. And the web service, we'd have an admin interface and say, this counter has this volume of water associated with it, and calibrate it at that length. That never really got implemented. We also have support for cameras, and we're going to start processing camera information within the web service. That still might come there. So we had all these things called non-processed units, or n-star units. And those are all kind of still in there. Not all of them have been implemented or partially implemented. And there's also this problem with all of the GPS data is done statically. So we didn't have time to really hook up. Since all of these were pretty much stationary, we focused more on getting all the sensors out there and didn't focus on GPS. And we had GPS, USB GPS transmitters. We just hadn't fully implemented them. So all the data for the sensor locations is just statically uploaded into the web service in that when we load the data in the DDL phase. And so one thing that we wanted to get to is the point where we could actually transmit the location in each data package. And that way in the web service we can keep track of if it moved at all. And there are applications for that. There are a lot of Arctic sensors, for instance, that are actually on glaciers. And they keep track, every time they power up, they all send their GPS data to see how far they've actually moved. So in the future, other things that we're looking at, the old team, we're looking at adding in self-registration. So all of the routers could actually register themselves. Right now, we have to give them a public-private key pair. And in the future, we just want them to be able to generate their public-private key pair and only send off their public key and register it. So anything could register with our service. And so if we get bad sensors, we could just delete them and ban them. But we know that everything that's coming in from the sensor is at least coming in from the same sensor each time. We want to support more sensor types, such as light sensors, pH sensors, anything that you can automate sensing. And also supporting more formats, such as JSON, WaterML, even KML. We talked about doing this in the web service, and we also probably want to do this on the sensor relay itself. So you don't have to tie LtSense to BigSense. You can use LtSense and use KML and send it straight to Google Maps or Google Earth, or use WaterML and send it to a national research web service. So there are other programs out there that are trying to do the same thing, lots of them. Two of the others that we're looking at right now, one's called Data Turbine. It's written in Java. It's just a web service. It's a really thin web service. So the one I wrote, it runs on top of Tomcat. But Data Turbine is a thin one that's just a simple jar file, and it pulls in data. And it's designed to be able to sample all kinds of data, streaming data, including video data. And it's open source. So you can run it on your own service. You can just download and run it. Another one is called PashTube. I think that's how it's pronounced. They provide a way that you can stream stuff to their servers, and they make all kinds of pretty graphs for it. I don't believe they have a version you can download. I think it's all streamed to their service. It's one of those software platform as a service things. So the advantage is it's just out there and you can hook into it. The disadvantage is if anything happens to them, you could lose your data. But they do have standard ways of pulling out your data, so you can back it up from them. And we do have a publication coming out. It's been submitted, and it should be published soon if we survive the peer review process. It's called Monitoring Permeable Paver Runoff with Sensor Networks, and it's going to be in the International Journal of Digital Earth. The source code for everything is up here on these websites. BigSense, BigSense Tester, LtSense, and the Diject framework. Diject also has its own website, diject.com. And that's all I got for you. So, questions?
If you, if you wanted to do another implementation, I understand that routers were, a good idea in the sense that they were cheap hardware, but would you consider using something else altogether for that part of it?
That's a really good question. So there was a startup company that formed out of this, and they started looking at different things. Early on, I thought that the routers are really nice because they are extremely cheap and they are extremely powerful. So the standard Linksys router, especially on the high-end Linksys routers, one of the ones we looked at, the 2100L, it had I think it had a 400 megahertz MIPS processor in it. They have about 32 megs of RAM. They have quite a bit for an embedded system, especially compared to embedded boards that you buy. If you look at Beagle boards and the other Linux embedded boards, some of them can cost up to $150 to $200 to $300, and they barely have what's some of them have below what's on these boards. But a lot of them do have a lot of specialized things. They have input-output pins, which are really nice. With these, we'd have to use the serial interface or solder on our own pins. Or use USB to serial adapters, but a lot of the hobby boards have input-output pins. They can usually take a compact flash card, so you're not limited to OpenWRT. You can put in much larger Linux distributions. If I had to do this again, I would look at other solutions, especially with things like the Cherry Pi that have come out. Even though the Cherry Pi has been in so high demand, it's been hard to get a hold of. A lot of other boards have come out like the Cherry Pi. It's brought down the price of the embedded market. So these boards that used to cost $150, $200, some can cost $80, $60 or less now, and they're just as powerful. And it's really nice to actually have input-output pins on board, because then you can support all other kinds of sensors without having to wire your own analog to digital converters and getting breadboards and putting all that stuff together.
I have another one.
Right.
I really have got a dislike of XML. So when I saw you do XML, I said, well, what you do? And so, I mean, my guess is that you had Java at the other end, so that was where the XML came in. It seems to me that's kind of legal framework for Java. That's not the right.
Yeah, and it was in Scala, so Scala had some built-in XML parsers, so you didn't have to add in any libraries. I just used it at the time, but we actually are working on JSON implementation too, so that's probably something we'd go to in the future, just especially because the packets would be smaller. For as few sensors as this, it doesn't really matter, but if you get to a lot more sensors, then it would be nicer to have smaller packets.
But
why would it be missing XML?
but the Java component of it at all, was that just because you were comfortable with Java, or because there was someone else had already done that part of it
So I wrote the web service too. The service was actually written in Scala, and it was just because I picked it just randomly.
Right.
So this ended up being it was a non-profit to start off with. So
right. I've forgotten. Sorry, Scala is a JVM thing.
Yeah, it runs on the JVM.
Yeah. Okay.
Yep. What else? All right, cool. Thanks.